Well, welcome everyone. I'm going to get started. So thank you all for taking some time out of your day to sign in for today's webinar about the Altair solvers. For those of you who don't know me, my name is Drew Buchanan. I am a senior applications engineer with True Insight, who is the North American channel partner for Altair. As I kind of go over a couple intro slides, I'm just going to kick off a poll. Feel free to work your way through answering either of those questions. It just gives me a good understanding of if you're using CAE, and just for your information, CAE would be FEA, CFD, or any type of simulation tool, yes or no, and then also what type of tools you're currently utilizing. So great, thanks again. So those of you who don't know who Altair is as a company, Altair is a really a partner for engineers and designers where you can sort of leverage simulation, high performance computing, and AI to solve a variety of challenges. And we'll kind of cover that today as we work our way through the presentation. So first thing, really, this is kind of give you a broad scope of the different types of solvers. We'll be focusing in on OPTISTRUCT and RADIOSS. But Altair has a number of solvers, and I'm going to show you a couple of different solvers, but also along the scope of solvers, Altair has a number of solutions, even outside of traditional physics simulation. And that could be data analytics and AI. So we have a number of customers and financial services or analytics and IoT, and even looking at, ID or design modeling. So point being is we love to talk to customers. If you have any type of challenge you're running into, let us know. We probably have some type of solution there for you. And kind of segueing from the last slide, again, if you're unfamiliar with Altair, we've been around since the 80s. We have a number of customers pretty much in every sort of industry you can think of. And that just kind of speaks to the product suite that Altair has and a number of solutions that are out there. Great. So looking at the poll, great. So it looks like the majority is using a CAE tool. And I really appreciate those of you going through it. I'll let the poll last a little bit longer. So it looks like, there are some Altair users here, great. And then some other external solvers, which is great too. So our agenda for today's webinar, we'll first talk about Altair 1, and then we'll jump into the actual solvers. And I'll try, I have a number of demonstrations to show for each of the solvers. My colleague is actually in the chat. So if you do have any questions as I'm running through the webinar, he's readily there answering questions. And at the end, any questions that my colleague hasn't answered, I will address. So feel free to ask questions as I work through this. And definitely at the end, there'll be a Q&A session if you have any further questions. All righty. So the first thing, I always like to sort of point this out because I think this really kind of is very unique among simulation tools is Altair 1. Altair 1, the way the licensing model is set up for Altair is it allows you to leverage different solvers. So I know there's a number of users within this webinar who are Altair users, but some of you guys may not even realize that you have access to a number of other solvers within your suite. For those of you who are new to the Altair architecture, some of the other kind of competing tools out there, you have to purchase individual modules. Altair, you're purchasing units, which gives you access to every Altair product. So this allows you to kind of leverage different solvers, which is what Altair wants you all to do. Is whether you're trying to solve an implicit sort of structural study to looking at an impact or explicit study, you can kind of leverage those tools very easily within the suite. So we'll first start on manufacturing solvers. I'm not going to spend a ton of time, but I do think it's pretty useful to kind of take a look at manufacturing solvers. So when I say manufacturing solvers, what am I talking about? Well, these would be if you have any manufacturing process within your company, we have tools that simulate these exact manufacturing processes. So looking at casting simulation, that could be gravity casting or high pressure, low pressure casting, metal forming, looking at sheet metal forming, hyperforming, and then extrusion, die extrusion for both metal and polymer. molding simulation, which would be traditional injection molding, or even polyurethane, which is more kind of niche specific, and then additive manufacturing. The nice thing about all of our tools is they're integrated into the Inspire interface. So we'll take a look at one of the tools specifically for metal forming. What that means is that these simulations are set up to be pretty easy to run, but they're leveraging the power of, for the most part, OPTISTRUCT and RADIOSS. OPTISTRUCT being an implicit solver and RADIOSS being an explicit. And if you're unfamiliar with those terms, I'm actually going to go over what an implicit and an explicit solver is in a few minutes. And lastly, again, this isn't, I'm not focusing in on manufacturing solvers in this webinar. So I'm just going to show a quick example, but bear in mind that we can leverage lots of different types of processes for each of these tools. And if you have further questions about it, just let us know. We can definitely sort of address what those questions could be. So I just want to kind of show a quick demonstration of one of the manufacturing solvers, which is actually Inspire Form. Inspire Form actually leverages an explicit solver, which is RADIOSS, and that allows you to kind of simulate, in this case, sheet metal forming. So if we actually take a look at this, a couple things I'll point out. Across the board in the Altair suite, we are able to we're CAD and sort of solver agnostic. What I mean by that is we can import various CAD formats, both kind of the major kind of CAD formats as well as neutral file CAD formats. So in this case, we can import our sheet metal, and this is a spring back analysis. If you're doing any type of sheet metal forming, or if you're working with any of your manufacturers, you're probably familiar with spring back or crash forming. The great thing about this tool is there's a pretty easy GUI. It's set up by the ribbons options right here, where if you need to make geometry changes, even within our tool, you can. So maybe you need to make an extrusion or sort of adjust a draft, what have you, can do that. And then we can kind of go over to the actual analysis section, which is under the feasibility and tryout section right here. The process of going through this is, specifying your material properties, and there's a number of sheet metal materials into the database. Across the board in all Altair tools is if it's not in our database, you can easily add a material to the database. And then you go through the actual operation process, and there's a number of processes we can add right here. Like I said, this is a kind of a traditional crash form with a little bit of spring back. So if you're unfamiliar with that, if you've ever kind of formed something, the tendency after you form it, like think of a paper clip, is that kind of springs back, it kind of goes back to its original shape. We can actually simulate that process within this tool. So as far as post-processing, what you can kind of take a look at after we run this scenario is we kind of simulate the actual forming process directly within the tool, where the sheet metal blank is coming down and being formed accordingly. So it is using an FEM-based approach and then solving directly for things that you would typically look if you're concerned about forming, which would be thinning, what your overall thickness is, and even being able to see if can this easily be formed. These are values you'd be able to see within our tool. Okay, great. Like I said, I didn't want to spend too much time, but just kind of give you a feel for some of the manufacturing solvers. So I want to spend a little bit more time on the structural solvers here, kind of the focus of this webinar. So when we speak about structural, and this is across the board in FEA, you'll probably have heard the term before of implicit and explicit. And so this is not an Altair specific term. This is just an FEA speak. So we have a couple equations right here. I don't want you guys to have any bad memories of engineering school, but these are kind of the basis of FEA. So we have our equation of motion, F equals Kx. And then we have our equation, that F equals Kx is for typical static applications. And then our next equation of motion is for dynamic applications, where you have our mass matrix, our damping, and then also our stiffness. So specifically what implicit is doing, it's solving at every single time step. What this means is that it's solving, when we kind of break this down, you kind of see all these are matrices. And when you're running through FEM, in any tool, you're creating a mesh, and all these have nodes, and you're integrating and going through partial differential equations to kind of calculate everything. So implicit can be very useful for static applications or some dynamic applications, but generally when your strain rates are less than 10 to the negative 3 per second. The reason being is because what's really happening is, if you ever looked at mathematical proofs of an implicit solver, it's really looking from one iteration to the next iteration of being within a strain tolerance. So that's why across the board, whether you're working in Altair or ANSYS or Nastran, there's nonlinear convergence criteria when you're running an implicit solver. So that's how large your strain can be allowed for each individual step. So yeah, global equilibrium is verified at each time step. So what this means is that your results are going to be very stable, but every single increment has to converge. So if you have something with very high strain, like an impact event, it's going to be very difficult to solve at an implicit. It's probably going to be impossible, or it's going to take a really long time. So what explicit is, it's really solving for the acceleration term, this x double prime term. And because the mass matrix is generally lumped. So that means the integration can be pretty easy. So you're just solving for accelerations. So it kind of eliminates some of your sort of matrix inversion issues that you would have in typical implicit applications. When you want to use an explicit, explicit should be used typically when your strain rate is greater than 10 to the negative 3 per second. A good example of an explicit would be an impact study. So if you ever see a car crash simulated in simulation, that would be explicit. Any type of ballistic event or explosion, that would be explicit. Implicit would be, traditional kind of like a bending example or something that's it's still very nonlinear, but it's more, it's not as high energy. A couple other applications that I have used explicit in the past would be maybe something that's not like a ballistic event, but maybe something where there's a lot of energy transfer really quick, like maybe a snap through problem. That, high contact, explicit can help in that regard. One of the things that explicit you should be aware of, because you're calculating the acceleration, convergence criteria are not checked at every single iteration like implicit, but as a result, your time step has to be very small to get accurate results. You're calculating the acceleration at the nodes, so your time steps have to be pretty small. That's a quick overview. If you have more questions about that, send them in the chat. I can talk about it, but these are kind of the basis of most structural solvers, implicit and explicit. So when we look at our structural solvers within the Altair suite, there are two solvers. There is OPTISTRUCT and RADIOSS. OPTISTRUCT traditionally has been an implicit. Note in 2020, they did add an explicit dynamic capability. So there is some explicit capabilities there. But for the most part, when people talk about OPTISTRUCT, OPTISTRUCT is looked at as an implicit solver. So implicit has a lot of different functions. You kind of see a bunch of functions. I'm not going to go through every single function right here. But typical nonlinear static, linear dynamic, some thermal analyses. One of the things where Altair has been specifically powerful is optimization. OPTISTRUCT started as an optimization solver when it was developed in the early 90s. And we have so much capability there in terms of optimization. Not only can we do the typical structural FEA and thermal FEA calculations, but we have optimization, and we have that capability of optimizing across various types of studies. I'm going to step through an example for composites, just kind of a more unique example of using optimization, but we can take advantage of all these different types of optimizations even within composites. The final thing I like to point out with OPTISTRUCT, because again, when I look at other structural tools in the market, it's not something that's always available, is NVH, which would be acoustic solving. So NVH standing for noise, vibration, harshness. It's a real common test that maybe some of you guys are doing in the automotive or aerospace industry. So we have that capability to run acoustics as well with OPTISTRUCT. So let's take a look at an example. We'll jump into HyperWorks right now. And we'll take a look at a specific composite example. So again, for those of you who are a little bit newer to the Altair suite, Altair kind of really spent a good bit of time updating the interface. I ran a webinar a few months kind of showing the newer interface. That's on our YouTube. You can check it out. But I'm going to be running everything in the new interface. So some of you legacy guys, you can still use the old interface, and you can run OPTISTRUCT within that interface. First thing I'll point out, obviously, is the capability of importing. So this is kind of what I was talking about earlier in terms of solver deck. You can bring in a whole bunch of different solver decks. They're not limited to just OPTISTRUCT, or you can create a solver deck, which is what we're doing in this case. The other thing to kind of bear in mind is you can also export to different solver decks. Maybe you're setting an OPTISTRUCT, you're going to run it with an OPTISTRUCT, but maybe if you want to run in another solver, you can do that as well. So the way you go about sort of setting up this problem is actually a composite model. You actually can look at our individual plies right here and review them if you want, where you can specify the individual plies. And these are just based off of the different shapes we're kind of looking at. If you're dealing with composites, definitely something where OPTISTRUCT does a really good job in terms of looking at the tool. But as far as the actual individual study, we've meshed this study within OPTISTRUCT using the power of hypermesh, where you can kind of control your mesh at everywhere in the system. And then we specify our specific boundary conditions. In this case, we're running an optimization, but we're running it based off of a couple, just a couple loads and restraints on the system. So if we actually take a look at the loads right here, you can kind of see it's just a couple of point loads right here on the end, right here. So kind of a traditional implicit loading scenario. The way to apply loads within OPTISTRUCT, we have a nice kind of toolbar right here where we can just kind of click on our edges, surfaces, even on entire parts. We can do that in terms of defining our loads. And also, we're not bound by just using loads within nonlinear. We can also enforce displacements. So if maybe you don't know the loads you're applying, but you know the actual final desired displacement, we can apply a displacement and then solve for our reaction forces or our forces that would occur in the system. So in this case, in this OPTISTRUCT case, we have loads on the one end and we are restraining the other end. We're building up our ply stack up and we want to run optimization. So when we actually take a look at this, we can define our plies by clicking on the surface and specifying, what our thickness is and what our material properties are. So, if I look at my material properties, it's just a carbon epoxy with our engineering criteria keyed in. And then our loads, which we've already gone over in terms of restraints. The other kind of really nice thing about OPTISTRUCT is there's a number of ways of controlling convergence. This is known as cards. Very similar, and OPTISTRUCT is built off of, it's a much sort of better performing Nastran. Some of you analysis guys probably are familiar with Nastran from the 80s. Cards allow you to kind of control convergence within OPTISTRUCT. So in this case, I just have a composite output card. So actually outputting composite data. And then just some typical kind of case controls, which would be, specific convergence criteria. So again, not going to spend too much time on this because could probably spend a whole hour on just cards. But one of the cool things about OPTISTRUCT is the ability to control various values in terms of how you're solving. All right, so let's take a look at some of the results. I ran this case. One of the nice things about Altair, again, in terms of updating the interface, there's a lot of nice post-processing and reporting built into the HyperWorks interface. When I actually kind of create a contour plot right here, I can specify what components I want to apply. In this case, there's just obviously our ply components, but we can look at them. And then I can actually look at my composites. I can look at the individual layers. I have different plies and I can plot this. I can see what my composite strains are for each of my individual plies. What my strain angle is going to be, my von Mises strain. So various things that you would want to look at from a ply perspective. Additionally, if you're running, in this case, I ran an optimization, you can actually obtain from the output what your optimum thickness could be. We started off with kind of a default thickness for all of these, but we could run an optimization to kind of characterize what that thickness would be. Great. So let me jump back to my PowerPoint here. And let's now talk about our other solver, which is RADIOSS. Similar to OPTISTRUCT, RADIOSS has traditionally been known as our explicit solver. Note there are some implicit capabilities. You know, what I typically recommend customers use OPTISTRUCT for is traditional implicit. And then high energy events is where you use RADIOSS. Obviously, like I said, OPTISTRUCT has an explicit capability that was added in 2020. The only reason why it's added is there's certain material laws and material cards that are within the OPTISTRUCT lingo. That's why that feature was added. But it's not as powerful as RADIOSS. RADIOSS has been an industry leader. It's been around for a good bit of time for crash testing. That's kind of where it came out of in the automotive industry. Shock and drop testing. So for any of you guys who are doing any type of, it doesn't have to be automotive, but anything with any type of high impact. For those of you working in consumer goods, this would be like, consumer goods drop testing. We can characterize that within RADIOSS. We have the capability to kind of use advanced multiphysics. This could be, hydrodynamics or FSI for RADIOSS, which is nice. And then we can also characterize quasi-statics. I already mentioned, those of you who've been doing analysis for a while, if you've ever run into any convergence issues with nonlinear static, specifically with high contact problems, it might be useful to jump into explicit. That's sometimes a good alternative to kind of get those problems to solve. So let's jump into an example for RADIOSS, for those of you who may have not seen RADIOSS. All right. All right, great. So one of the things that's pretty nice about the interface here, again, within RADIOSS, it's focused around dynamics. In this case, it's actually a front bumper, and we'll take a look at the results in a moment, but I kind of want to go over some of the tools. So one of the things that's really nice about the HyperWorks interface in terms of solving is you note that the analysis tab automatically updates based on the solver interface you're working in. So what I mean by that is I can change my solver interface. By default, when you have HyperWorks, it defaults to OPTISTRUCT, which is the implicit solver, because that's the majority of cases that customers are running. But if you can go down and change it to RADIOSS, and then we have a bunch of our other solvers, like FICO would be our electromagnetic solver. HyperExtrude would be one of our manufacturing solvers. So we just changed our solver interface to RADIOSS, and we know when we go to our actual Analyze tab, this is where you kind of see we have a couple of additional boundary conditions that aren't in the traditional OPTISTRUCT boundary conditions. So this would be your velocities and accelerations. So in this case, when we actually look at our load criteria right here, we can actually look at our velocity criteria where we're kind of hitting our bumper right here. Moving at a speed of, I think it's 5 meters per second is what this case is for this bumper. So the nice thing about these tools is you can, easily specify, click on the icon or velocity, and then specify, what value you're going to apply within the system. We also can take advantage of initial conditions. Those of you who've run explicit studies know you may have like some type of impact, some type of characterization that's, initially it's might be moving at one case and then move somewhere else. And then even looking at some explosive boundary conditions as well. So I'm going to actually kind of look at our results now. A couple other kind of things that some of you legacy Altair users, you may not have seen this before, but when you're in HyperWorks, if you remember from the old interface in HyperMesh, there'd be the icon right here where you could switch to HyperView. You can still do that in the new interface. So I'm going to go to HyperView, and I'm going to load the results for this case. So HyperView, for those who are unaware, is our advanced post-processing tool. What I was just showing you before for OPTISTRUCT was the built-in kind of post-processing, but we have actually the ability to look at even more advanced post-processing, which typically is the case for most explicit models, is you want to look at kind of advanced post-processing. What we need to do is just load our results now. So if I come to my model here, I'm just going to load these real quick. So what you'll kind of see when you load these files is you'll see our actual file size right here. And this is our post-processing file we're going to take a look at. So I'm going to hit apply. And one of the really cool things about Hyperview is the transient animation tool. When you're looking at explicit cases, we have a number of time events. So specifically, what our time steps are. We kind of talked about how important it is to have our time step, but if I animate this, kind of see directly what's happening. This is when you guys are thinking about your studies, when you would want to use RADIOSS or an explicit solver is an event like this where you have so much strain or deformation happening. Like in this case, it's our bumper running into a rigid pole. Within our actual tools, obviously, we can actually take a look at specific results. You know, I could look at our von Mises stress. Nice thing about this is being able to, you know, I can look at my actual element criteria. One of the things that generally tends to be very useful in explicit studies is making sure you have a good mesh along the contacting area. And so we can turn on our mesh in post-processing and make sure if we're sort of seeing any erratic results, that might be where we might want to sort of adjust our mesh accordingly. So everywhere in the system, we can take a look at our von Mises value, our strain value, even taking a look at specific velocity values if we want to look at what our velocity is at a specific step, which could be super useful in the explicit case is trying to understand what your velocity and acceleration is at a certain time step. And so as far as post-processing, that's our results. I just want to kind of touch on, let me come back to the overall model. I want to kind of show a couple cards as well, things you'd look for within RADIOSS. So let me just open up that model. So like I said, the boundary conditions, obviously there's different boundary conditions, but there's also specific cards for explicit where you kind of want to characterize, specifically what you want to include in an output file and any specific criteria in terms of what your energy or scaling you want to do. Typically, if those of you have run explicit, one of the things is you might do some sort of mass scaling in terms of helping with the integration. You can control that. So again, very similar to OPTISTRUCT is we have these abilities to kind of control parameters to help with convergence. Otherwise, you'll see that the model tree is set up pretty familiar. One of the things you'll see here is we specified that rigid wall, which is pretty cool. We can look at individual parts and specify rigidity. And this is exactly what we'd be running in a explicit study is looking at impacts. So we have this cylinder we just modeled and I'm specifying that as fully rigid. And then a couple of other things here. Just looking at individual output values. So again, I kind of showed through that in Hyperview, but specifying solving for acceleration and velocities, what have you. Great. So let me jump back into my tool, my presentation. And I'm going to touch on fluid dynamic solvers. So one of the things that RADIOSS and even OPTISTRUCT is they couple with our CFD solvers. So specifically for, like I remembered sort of seeing on the slide NVH, noise, vibration, harshness, maybe coupling with a CFD solver there, or even coupling for thermal FSI, and there's a lot of different applications. RADIOSS can be coupled for some fluid applications. So there's a lot of value in being able to integrate the CFD tools with both OPTISTRUCT and RADIOSS. So those of you who are existing Altair customers, you probably are aware of some of the tools you have, but you may not be aware that there's actually a number of CFD solvers within the Altair suite. The legacy solver that most of you probably are pretty familiar with, if you know Altair's AccuSolve, it's the default implicit Navier-Stokes solver. So what you'd sort of see for typical fluid flow and heat transfer applications, obviously it can run both transient and steady state applications, ability to model incompressible and compressible fluids. And really, when we're speaking to OPTISTRUCT, and RADIOSS has that ability to be coupled for FSI and thermal FSI. It uses a more FEA-based approach. In CFD, you have the choice of FEA and FEM. With an Altair, we actually have CFD solvers that are capable of both an FEM and FEM-based approach. So in CFD speak, that means you're modeling kind of through a finite element method like you do in traditional structural solvers, whereas a finite volume method is you're kind of creating a cell. So we have tools that handle both of these. Electroflow is an example of a finite volume solver. It's another implicit Navier-Stokes solver, but it's really geared towards chassis design, boards, and lots of components for PCBs or joule heating. So if you're dealing with any type of electric kind of thermal analysis, this is a really powerful CFD solver that can handle that. The last two solvers are more advanced CFD solvers, NanoFluidX and UltraFluidX. NanoFluidX is an SPH particle solver. So SPH would be smooth particle hydrodynamic solver. That would be like if you have any like fluid, it was developed for like fluid in for pistons. Like a good example, analog example is think about a water tanker going down the road, sloshing around. There's an interaction of the gas of the air in the tank and the water sloshing around. That's a free surface solver, and we have that capability. So typically that's for multi-phase applications for NanoFluidX. When you have a liquid and a gas interacting, that's a good solver to handle that. We also have another solver, which is for a lattice-Boltzmann solver, which is UltraFluidX. This would be if you're doing any type of vehicle or heavy-duty vehicles. The great thing about this is it leverages GPU. It can really solve large systems for aerodynamics. So if you're doing wind tunnel testing, that's a solver that can really help and aid in that. So let's jump into a demonstration. I wanted to kind of show a more unique example. I've showed in a couple webinars looking at AccuSol, but I wanted to kind of take a look at Electroflow. So Electroflow, it's used within SimLab. What I was just showing for OPTISTRUCT and RADIOSS was within HyperWorks. SimLab is another multi-physics tool like HyperWorks, meaning that I can actually run OPTISTRUCT and RADIOSS within this tool. Those of you who do have Altair licenses, if you haven't used SimLab, it's definitely very powerful. I ran a webinar on SimLab a few months ago. Feel free to check that out. So the value of running this Electroflow CFD solver is it's capable of looking at components on a board. Typically, if you have a small component on a PCB, it might be kind of difficult to mesh. With Electroflow, it's using a finite volume-based approach where it kind of makes these square cells, and that's how it sort of discretizes the data. Why this is very useful is if you have a PCB with hundreds of components, which is generally the case with most PCBs or electric cooling tools, it can model these and mesh these efficiently and then actually run through a thermal analysis. So first step is we mesh our tools. As far as meshing goes within the tool, this Electroflow tool is built for PCBs, so you can specify your layer definition, how many layers you have or vias. And then we can actually take advantage of our component definition. In terms of bringing in an ECAD data, it will automatically recognize those specific components accordingly. In this case, this CFD solver is used for thermal applications. We have a number of tools. We actually have forced convection. We have our fan being applied here. So we can actually apply a PQ curve, which would be our CFM. If you ever looked at fan curve data, we can key this value in terms of our volume flow rate with respect to pressure. On the actual fan, we can key that in. We have a number of heat sources, which are all these individual components which you have on our PCB. This would be how much power or heat dissipation. So in this case, 4 watts for this specific component at 1 watt, and can really discretize all your individual components how you see fit. Some of the other really nice things about this is those of you who are doing this type of design, looking at thermal resistances, you can key these in, and then also using kind of an accurate kind of characterization for your chip, which would be a 2 resistor model, which has your thermal resistance and also your total heat dissipation. When we actually go through our results, again, the post-processing within Altair makes things very useful. You kind of see I was hiding a couple of the actual outer enclosure boxes. I can still hide those if I want. So if I want to hide them, I can hide the chassis, and then I can just look at the individual board. In this case, I can specifically utilize some of the advanced kind of post-processing features within SimLab. In this case, maybe I can do some ISO scaling. So if I want to apply a temperature value, I can sort of adjust this. You see how I move it to the left? Everything that's showing is at 293 Kelvin or below. If I go up, it means everything that's at 341 and above. And I'm sorry, I said earlier below, it's actually above, but we can change it to be below. So what you're seeing right now is everything's at 341 Kelvin or above. So really helps you understand and localize where these key values can kind of be. And again, kind of speaking back to our structural solvers, is these CFD solvers can be coupled with our structural tools. Great. I'm going to jump into back my presentation here and speak about some of the other Altair solvers. So across the board, there's a lot of different solvers within the suite. FECO is our high frequency electromagnetic solver. If you remember earlier when I was running through the OPTISTRUCT example, it actually had the FECO interface. So you can actually mesh within HyperMesh, HyperWorks, and then send that mesh to FECO. Typical things you do in high frequency if you're designing for any antennas or looking for any type of radiated emissions, that's where you'd use FECO. Flux is one of our other low frequency tools. And again, the beauty of kind of stressing what these solvers are is if you're purchasing a license of Altair, generally if you purchase enough units to use OPTISTRUCT, you're going to have access to these other solvers. We kind of look at our solvers by how many units there are. Some of these solvers take less units, some of them take more, but for the most part, you're getting access to the majority of these solvers. So Flux would be our low frequency tool. Again, it's another electromagnetic simulation tool. It's using a finite element based approach. So you mesh a system. Those of you who are designing motors in the EV space, this would be a great tool for you because you can actually simulate those electric conditions, but also simulate the thermal conditions. Maybe if you're looking at the heat that would be generated and maybe a charging cable for your EV vehicle, we can simulate that. Motion Solve is our kinematic solver. This would be utilized for anything with rigid body dynamics, and that kind of, depending on what you're doing, again, I'm speaking on automotive, but I don't want to limit that. Maybe you're designing cams. Motion simulation would be a great tool. Another solver, a structural solver I didn't really spend any time with because it's not within the OPTISTRUCT or RADIOSS space, is SimSolid. It's technically an implicit solver, but it's using what's known as just a sort of derivation of implicit to actually not have to mesh systems. The beauty of this is if you've ever run any systems that are very, very large assemblies, or maybe you have a lattice structure, maybe you're doing a lot of additive manufacture, a lot of those systems can be very difficult to mesh. It's going to take a lot of time in OPTISTRUCT or RADIOSS. So if you're running into meshing difficulties, SimSolid is a great tool because it is meshless. Generally, when I talk to CA analysts, it sometimes gives them a little bit of concern, but it is benchmarked by NAFEMS. And if you have questions about it, we can talk a little bit more about the theory. That's not really the focus, but it can solve some of these large assemblies. And since it's implicit, it's looking at nonlinear static, static linear, and some dynamic cases. Kind of the last two solvers I have on this slide are POLEX. POLEX is a PCB analysis tool. It's really board specific, and the solvers it has are signal integrity, our power integrity. So if you're looking at voltage drop or current drop across your PCB, it can simulate that It also has thermal analysis capabilities, but this would just be for the board level itself. EDEM is kind of falls in that boundary between CFD and FEM. It's a discrete element-based tool, meaning that it's characterizing what's happening to particles. So if you're in agriculture or pharmaceutical and you're trying to see what happens to specific particles, it's very analogous to CFD. We have a solver called EDEM that handles that. There's a few other solvers I don't have on this slide. So we have a number of AEC or architectural engineering tools, which have structural tools built into them. So those, if you have questions or maybe you're in the civil engineering space, we do have structural solvers for that. And then also we have a bunch of more MBD-based tools. This would be, kind of block diagram system simulation tools. If you're in kind of the electrical engineering space, we have a number of solvers there. So I want to kind of take the last 10 or 15 minutes for any questions. A couple things I will kind of point out as I'm sort of reviewing any questions any of you guys have. Encourage you guys to check out our social. Our YouTube and our blog are consistently updated with more how-to information. So check those out, as well as our LinkedIn and Twitter. For kind of future webinars and cases. I'm going to actually be running a more kind of how-to webinar on hypermesh tips in the fall. I don't think they're posted yet, but they're going to be posted very shortly. So keep an eye out for that. But thank you all for attending. I'm going to stick around in the chat for any questions any of you guys may have.